Thanks for joining us on our second lesson of the photoelectric effect. We'll look at some calculations today. Now we've said in the previous lesson that our electrons is stuck inside a metal. This metal has got a specific work function which is indicated with W and a small zero, and that's the minimum amount of energy needed before these electrons will be able to be emitted from this metal surface. It also goes together with the threshold frequency, and we can go and calculate the threshold frequency or the work function if we've been given one of them. Now, our work function's formula says that it's equal to Planck's constant times the threshold frequency. And the definition for the threshold frequency was the minimum amount of frequency needed for an electron to be emitted from the surface of the metal. Now we also spoke about a photon yesterday that will be coming in. This photon, which is seen as packets of energy of light, will be having a symbol of capital letter E for its energy. And it said that all of its energy will be transferred to one electron only. Now the symbol for this energy, as we said, is capital letter E, but the formula for it will be Planck's constant times the frequency. Now we will speak about this a bit later on again. Let's just continue onwards. If this photon's energy is more than the work function, then we said our electron will be able to leave with a kinetic energy. And this kinetic energy was known, as you would know by now, as a half mv squared. Now, when our electron were able to leave the metal, which means that it had sufficient energy coming from the photon to pay the work function, and it leaves the metal now, we don't call it an electron anymore. We'll be calling it a photoelectron. So inside the metal it's still called an electron, but once it's received energy from a photon and it's able to leave the metal, we'll then call it a photoelectron. So do make sure that you use this term whenever needed after it has been emitted from the metal. Now, as said, the photon's energy is indicated by capital letter E, and we will have the formula as Planck's constant times the frequency. Now, Planck's constant is going to be a constant that will be given to you on your table of constants at the back of tests and exams, and it will be 6,63 times 10 to the power of negative 34. It's a very, very small number. Do take note though that our energy is always measured in joules. And seeing that our photon is part of our electromagnetic spectrum, it will then also have the formula of C is equal to frequency times lambda. Now you've had this formula specifically for waves before, but you had V, which stood for the speed, times frequency times lambda, was equal to frequency, and you had V before, which was equal to frequency times lambda. But the difference now is, because a photon, which is part of our light, is an electromagnetic wave, this speed will be a constant of 3 times 10 to the power of 8. That's how come we make use of the formula C is equal to frequency times lambda. So should they not give you the frequency, but they give you the wavelength, and you would need to go and make use of that to go and calculate the energy of the photon, then we'll have frequency equal to speed, which is 3 times 10 to the power of 8, divided by lambda. And then we will replace this new C over lambda, which stands for frequency, with my initial formula. And it then will end up becoming that E is equal to Planck's constant, and that's equal to, that multiplied by C divided by lambda. So the photon's energy can be calculated using your speed of light together with lambda as well. Now we have spoken about conversions before in previous lessons, but you'll come across it again in this lesson. Note though that usually lambda is given as a very small value, which can either be in millimeters, micrometers, nanometers or picometers, and you need to convert each one of them every time to meters. Now if I want to go and convert millimeters to meters, then I'll multiply by 10 to the power of negative 3 or divide with 1,000. If I want to take micrometers to meters, I'll times 10 to the power of negative 6 nanometers to meters is times 10 to the power of negative 9, and taking picometers to meters is times 10 to the power of negative 12. Now let's take a look at our metal again. We said that it will have a specific work function, which can be calculated using Planck's constant, which is still 6,63 times 10 to the power negative 34, times the threshold frequency. And obviously, work function in this case is a form of energy. It's measured in joules, and frequency is still a frequency which is going to be measured in hertz. Let's go and take a look at our photoelectron. Remember, the photoelectron is that part of the electron that was able to emit from the metal surface because of the sufficient energy received from the photon. So my photoelectron, once it's been emitted, it will have a kinetic energy, which will be equal to a half mv squared. Now, kinetic energy is an energy, so it will also be measured in joules. But what's important to note there is that we would need the mass of an electron. Now, the mass of the electron is also a constant that will be given to you on your table of constants. And that's 9,11 times 10 to the power of negative 31 kilograms. So once again, if they would go as far to ask you to calculate the speed of the electron, note that you do have the mass of the electron. It's 9,11 times 10 to the power of negative 31. Now let's go and take a look how all of these formulas come together. Let's start off by saying that we've given our photon that has 100 joules of energy to be shown onto this metal surface. And we'll say the work function of this metal surface is 80 joules. So that means the photon with 100 joules will give all of its energy to this electron. The electron will use the 100 joules to pay 80 of it for the work function so that it can leave the metal. Now once it's left, the photoelectron has now got 20 joules of energy left, which will be used as kinetic energy. So from this, we're going to be able to deduce a formula. And the formula will state though that the energy here of the photon of 100 joules is equal to the 80 joules of the work function plus the 20 joules from the kinetic energy. So the kinetic energy and the work function's energies added up again will give me the energy of the photon. And this is the formula that we'll be making use of to go and do calculations in the photoelectric effect. And obviously, depending on what has been given and asked, you can go and break this energy formula still down into h times f, or h with speed of light divided by lambda. Your work function can either stay as work function, or it can be broken down in your Planck's constant times the threshold frequency, and your kinetic energy can also be broken down, for example, into a half mass and velocity squared. Now let's quickly take a look at the intensity of light. Now when we refer to the intensity, we're basically going to be referring to the power rating of a bulb use of light. So let's start off by saying that we've got a 50 watt bulb. Remember, watt is what we make use of to measure power in. And we're going to put it now a 100 watt bulb of the same color of light. Now we have now doubled the power rating. So that means we've doubled the intensity, and when doubling the intensity, it means we are then doubling the amount of photons coming in. So instead of having 2 as an example, we'll now be having 4. Remember that each one of these photons only strike one electron and give its energy to only one electron. So if I had a 50 watt bulb, then we would have had, in this case as an example, 2 photons coming in, striking 2 electrons. If these photons had, in this case, an energy that was greater than the work function, then we'll have 2 photoelectrons leaving at the end of the day. On the other hand, if we then doubled the power rating, we'll now have 4 photons coming in, which means 4 electrons will then be affected, and obviously if the same color of light is used, then the energy is still greater than the work function, and now there will be how many electrons leaving? 4 of them. So by increasing the intensity, we're increasing the amount of electrons, which we call the photoelectrons, being emitted from the metal surface. Now electrons is seen as charges that will run around in a circuit. So if I'm then going to have a higher amount of electrons, it means an increase in the current. So that means if I go and increase the intensity, I'll have an increase in the current, seeing that more electrons will be emitted. Do take note though, that these electrons emitted will still have the same energy as originally. And what we mean about that, let's say we set the photons at 80 joules of energy, the work function in this case was 60 joules of energy, then they will be able to leave with 20 joules of energy. Now by increasing the intensity, we still use the same light, so that means the same photon energy of 80 joules, and that means that they will still be leaving with 20 joules of energy. There will just be more of them leaving with 20 joules of energy. Now let's just quickly go and explain the application of the photoelectric effect in our everyday life. Note though that this is a very simplified diagram though. You'll see that we've got a glass block or object here, which is going to have the cathode and the anode. That basically just means the side connected to the negative of my battery. Remember, the short line is negative and the long line will be positive. So that means in this case, this shaped convex type is connected to the positive. Now it doesn't need to be the shape, it just helps in catching the electrons, you'll see. Now this is going to be my piece of metal which we're going to shine a light onto. So we're going to have a beam of light coming in. If obviously this light's energy is greater than the work function, then there will be electrons emitted. So then we've got electrons being emitted into the space. Remember, electrons is negatively charged, and this side of my metal is connected to the positive of the battery, and a negative and a positive will attract each other. So therefore my electron will be attracted towards this positive part, and then it will run through the circuit. And that means we've got continuous current in the circuit. If the light did not shine onto this piece of metal, then there would have been a gap, and your electron will not have been emitted from the metal surface, and no current would have flown through the circuit. But the moment that light shines onto it, it emits electrons. Electrons are attracted to the positive, and the current runs through the circuit. Now, it's in this principle that many of our burglar alarms, as well as our smoke detectors and sliding doors work. So, if you typically look at the sliding doors at malls and shopping centers, then there is a thin beam of light just before you reach the door, which you can't see though. But when you are actually walking past this beam of light, you are interrupting the light, which means that that light then suddenly can't shine onto this piece of metal. That means that electrons can't be ejected and that there's no current flowing in the circuit. That means that the door opens up. At the moment that we've then passed through the door, then once again the light can shine onto this piece of metal unhindered, and then we're going to have electrons being emitted and again attracted to the positive, and the current then runs again through the circuit.